Can you hear me? Leah?
Yes, doctor. Yes, yes.
Oh, who is the chairperson?
Chairperson, Dr. Tan.
Oh, Dr. Tan is the chairperson. Okay. You can hear me then, okay lah.
Okay.
I thought sometimes got problem, right? Should I on the video or no need to on the video? Just off the video first lah. And then the audio off.
Hi everyone, I just land into this section. There will be a stage event. We wait for the participant to come. There is an ongoing stage event. Good morning to everyone. I hope those oral presenter for this section, please ask to share your audio and video, I mean the camera, so that we can start later for your presentations. All right. A very good mornings and good days to everyone here. All right. I'm Dr. Tan, the chairperson for this section. So the section is para section 4 with the title Sensing, Separation, Membrane Reactors, Nanofabrications, and Characterizations. Welcome to join the section. So before start to let the next presenter to present, I just want to explain a bit about the rule and regulations, just a brief rule and regulations. So all the oral presenter will be given 15 minutes for the presentation, followed by 5 minutes of Q&A. Okay, thank you for your kind operations. So I think we can start now. So the first presenter in our section should be Professor Dr. Ong Kiat Kim. So I will let the IT moderator to play her recorded videos. Please, IT moderator, you can play the Prof recorded videos. After that, we will proceed with the Q&A. Thank you, IT moderator.
Good morning, ladies and gentlemen. This morning, I would like to share with you my master's student study on methylphosphonic acid detection using DNA aptamer, citric nanoparticles. Chemical warfare agents are highly toxic synthetic chemicals. They can be dispersed as gas, liquid, aerosol, or powder. Nerve agents are organelles phosphate compound. They can block the function of an enzyme in our central nervous system. Nerve agents are the most toxic chemical warfare agent and has been used during wars and terrorist activity. This figure shows example of some of nerve agents, G-type, B-type, and A-type. VX, sarin, and so on can be hydrolyzed in atmosphere by water molecule to methylphosphonic acid. So detection of methylphosphonic acid are very important because it can be used as a marker to show the presence of this nerve agent. Colorimetric is one of the most commonly used methods to develop a sensor. Why? Because they have advantages. For example, convenient, simple, cost-effective, can monitor with the naked eyes, and can be used for on-site detection. The detection is based on color change using reagent in the presence of an analyte. Gold nanoparticles are strong candidates for colorimetric and optical biosensing of various targets. For example, nucleic acid, proteins, metal ions, and other small molecules. However, gold nanoparticle-based colorimetric have some drawbacks. For example, the result interpretation by naked eyes is less accurate as it's operator dependent and is not selective. So, how to overcome this problem? By using image processing technique, the accuracy of the detection can be improved. And DNA aptamer was used to improve the selectivity of the detection. This slide shows some of the previous study using gold nanoparticle-based colorimetric detection to detect pesticide. So you can see the color will change from red to blue or darker blue or yellow. Colorimetric detection also used for detection of nerve agent or chemical warfare agent. In this study, they incorporate with image processing technique to improve the colorimetric detection accuracy. Therefore, the objective of this study is to determine the optimum condition for detection of methylphosphonic acid by colorimetric attack sensor using response surface methodology based on phase, center, central composite design. There are three factors investigated in this study: concentration of citric AMP, concentration of DNA aptamer, incubation period for binding citric AMP with DNA aptamer. This slide shows the synthesis of citric cap gold nanoparticle. At first, we add gold 3-chloride trihydrate into a conical flask, then boil at 100 Celsius for 15 minutes at 1500 RPM, followed by adding trisodium citrate dihydrate into the solution. The color will change from pale yellow to dark red, which indicate the formation of gold nanoparticle. Then let it cool down to room temperature before centrifuge at 12,000 RPM for 30 minutes. And then the precipitate will be collected and stored at 4 degrees Celsius. This slide shows the experimental design for the detection of MPA. Table 1 shows the 3-factor investigate at 3 different levels: low level, center level, and high level. The experimental data response was used to develop a mathematical model which relates to the independent variable by using a second-order polynomial model as shown in this question 1, where y, beta naught, beta I, beta ii, beta ij, and xi or xj are the predicted response, constant coefficient, regression coefficient, for linear effects, quadratic coefficient, interaction coefficient, and coded values of the parameter respectively. The fit of the model was examined by determining the coefficient and adjusted R squared. This slide shows colorimetric detection MPA. Citric AMP was mixed with 1 microliter of DNA aptamer in 3 milliliter cap glass vial. The mixture was incubated at 37 degrees Celsius for different incubation period. The MPA was added until the mixture reached a total volume of 1 ml. After 20 seconds, the color of the mixture was captured using a smartphone at a fixed distance of 9 cm. The captured image was processed using ImageJ software to obtain digital value of red, green, and blue. Similar procedure was applied for detection in the absent MPA, which served as a blank. The captured image of the solution top view was processed using ImageJ software as I mentioned just now. The average value of RGB was used to calculate the response delta RGB by using this equation 2, where R0, G0, and P0 are red, green, and blue value of blank, while R1, G1, and P1 are red, green, and blue value of MPA. This slide shows the color change from red to purple when adding MPA into the DNA citric cap gold nanoparticle. The color change based on aggregation after adding this MPA into DNA citric cap AMP. Table 3 shows the experimental and predicted response as shown in this column. The result of ANOVA is presented in this slide. So you can see the model is significant. Factor A, D, P, A power 2, D power 2, and P power 2 are significant. Interaction effect between A and P, D and P also significant. However, lack of which are not significant, showing that the model can predict the response very well. In addition, the R square also high as shown in here. Table 5 shows the estimated regression coefficient, C values and P value. So this coefficient will substitute in the equation 1 and to get this equation 3. This equation 3 shows the empirical relationship between the actual factors and the response. Where Y show the response value of delta RGB, A, D, and P show the concentration of Citric A and P, concentration DNA aptamer, and incubation period respectively. Figure 3a show the interaction between concentration of Citric A and P and concentration of DNA aptamer. Increasing concentration of Citric A and P and concentration of DNA aptamer from low to center level resulted in the increase of delta RGB value. However, the response decreased when the detection was conducted at a higher concentration of A and D. Similar trend were observed for interaction between concentration of Citric A and P and incubation period, as well as interaction between concentration of DNA aptamer and incubation period, as shown in this figure 3a, 3b, and 3c respectively. In general, you can see that the maximum delta RGB were found at center level of this interaction. And finally, I would like to show with you the proposed optimum condition using this optimization plot. Okay, the optimum condition were concentration of Citric is 0.34 nanomolar, concentration of DNA aptamer is 3.9 micromolar, and incubation period is 18 minutes. I would like to make conclusion. The experimental data fitted well to the second order polynomial for prediction of delta RGB value. ANOVA results show that concentration of Citric A and P, concentration of DNA aptamer, incubation period for binding Citric A and P with DNA aptamer, interaction effect A power 2, D power 2, P power 2, and interaction effect between AP and DP were the significant factors affecting the delta RGB as indicated by p-value less than 0.05 and high coefficient determination R square which is equal to 0.994. And the optimum condition suggested by the RSN to get the optimum delta RGB value were 0.34 nanomolar of Citric A and P, 3.9 micromolar of DNA aptamer, and 18 minutes of incubation period. I would like to thanks to Ministry of Higher Education providing this FRGS fund to conduct the project. And we also like to thank to University Pertahanan Nasional Malaysia for providing the research facility. So this is the reference. Thanks for your attention.
All right. Thank you, Prof. Ong, for your pre-recorded videos presentations. So we will proceed to the Q&A slot. All right. So let me ask the first question to Prof. Prof, you can switch on your audio later. Prof, regarding your work, right? Can you tell me, is that the particles, the particle agglomerations in your preparation, is it will affect your prediction, your result? Do you consider the particle agglomerations?
Okay. Okay, can you hear me?
Yes, we can hear you.
Okay, yeah, I don't know how to show the slide. Okay, when we synthesis the gold nanoparticle, we add trisodium citrate. That one will give negative charge around the particle. Okay, so they got repulsion. There's no aggregation. So when we have the synthesized citrate gold nanoparticle, okay, it's still red color. Okay, So if you don't, that one is for citrate, trisodium citrate. We use there are two main properties, two reasons. One is as a reducing agent, and another one is a stabilizing agent. Okay. So I don't know whether okay, after we analyze, so the analyze will something like replace the citric AMP, so they will cause the aggregation, a change color.
Prof, since you are saying that you are using the trisodium citrate, right? They are act as a reducing agent and also a surfactant, right?
Reducing agent as a stabilizing agent.
Yeah, stabilization agent. Are you saying that you stabilize the particles so that they don't have, you want to prevent agglomerations or you want to have agglomerations?
Before detection, I don't want agglomeration. Before.
I see.
Before adding analyte. Okay.
I see.
Before adding our sample lah.
I see. Okay. All right.
Okay.
All right. I checked the questions from the Q&A coming from Dr. Motalik. Okay. Thanks, Prof, for your sharing interesting topic. I would like to know, why did you use the citrate gold nanoparticle instead of a gold nanoparticle? As a gold nanoparticle also give harder reaction with the DNA. So this is a question from Dr. Motalik.
Okay, I think I something already answered just now. Okay. We synthesis gold nanoparticle using by reduction method. Okay, using the trisodium citrate as a reducing agent and stabilize. Okay, trisodium citrate got negative charge. Okay, so when after synthesize, they got negative charge. So the gold there is no agglomeration. The gold still red color. Okay. After I add with DNA, I add with DNA, and they got bonding between the AU and sulfur, because the DNA I modify with thiol group, right? And then after that, I add with analyte. Okay. After adding with DNA, still got no color change. Okay. After I add with analyte, then got color change. Okay, because the DNA they got some conformation change from the coil to the rigid form, so they exposed to the medium, so cause the agglomeration. The mechanism, something like that lah. Okay, I don't know whether answer your question or not. The Dr. Motalik.
Yeah. Dr. Motalik, is that clear? If you want to ask further, you can put on your camera. It will be better if we have a live interaction.
Thank you, Prof,
Okay.
for sharing your answer. Just I want to know, in case of if we use the naked gold, without citrate cap, is it not give the color reaction? Because some research are also shown that they use naked gold, which complex with DNA can color change. Just I would like to know what is difference between the citrate capped gold and naked gold particles.
No, normally we synthesis gold, we use something, we have to stabilize the gold, otherwise they will got agglomeration. If you don't stabilize, they got agglomeration. So once they got agglomeration, before detection is this one is what we want agglomeration after the detection, not before the detection.
Oh, understand. To remove the agglomeration, to escape this, you use the capped,
We kept it,
understand.
stable.
Okay, thank you. Thank you.
Capping agent is capping agent.
Oh, capping agent.
Sorry.
So
Capping agent
to prevent
stabilize
the agglomeration, to prevent the agglomeration between the gold nanoparticles. Okay, thank you.
All right. We will select. There will be another questions. Prof, the question is like this way. May I know how do you select the characterization process and testing process for your product that is suitable for your for your product?
I'm not sure what
Are
do you
you
mean
clear?
product here. Your product here meaning which? I'm not sure.
I think maybe this question is like, what would be the correct what is the factor that so that you decide that your characterization process and your testing process for your final work to be applied in your applications? What
Okay,
is the factor decide?
I tried to answer the question first. I'm not sure it's correct. Okay, I'm not sure I answer your question first. Okay, I have characterized the sample before and after the detection. Before and after detection. So the normal detection, the normal characterization they use UVVs lah and TM lah. So both are done, but I just didn't show in this slide lah. In this presentation lah, both are done before and after detection lah. So what you can see, in UVVs they shift to the longer wavelength. The lambda max you see to longer wavelength. Okay, and then the TM you see before detection, after detection got agglomeration, the particle. These both are two characterization have done. Okay. I don't know what answer your question, right? You see?
Actually, yeah, correct. Okay, it's fine. And then, is there any questions, especially from evaluator? If, like, for example, Dr. Noro Aida, if you have any questions?
Hi, Professor. The interesting topic, but I thank you, but I don't know. I don't have a question, Prof, because it's not my.
Jangan lupa titik satu dekat.
I think that's all. And no more question, right, Dr. Tan?
Sorry, Dr. Tan.
Don't have more. Thank you, Prof.
Okay, thank you.
Sorry, Dr. Tan.
Dr. Tan, you are muted.
Yeah, but I can hear the echo. Is that okay? Right now it's okay. Fine. Okay. All right, then we proceed to the next presenter. So I would like to invite Ms. Obaid Asma Omar for her presentation with the title Go Nanoparticles with L-Cysteine as a Chiral recognition sensor for the Ketobrophene Enantiomer, right? Okay.
Yes. Assalamu
You
alaikum,
can start
everyone.
now. Yeah, you can start now.
Yes, I will start.
You can put on your camera. Yeah.
So I don't know if everyone can see my screen now.
Your camera is not on. You need to put on your camera.
Okay.
We still cannot see your screen.
Okay, wait.
Camera? Yeah, sure.
Okay.
All right. You can share your screen.
Okay. Good morning, everyone. So now can you see my screen now?
Not at this point. Can you reshare again your screen?
Okay. So I shared the entire screen.
Yeah, sure.
I don't know, it's just there is a cross red line on the screen.
Are you sure? You click share. You click share and then you just click share and share again, share entire screen. Or you can share your window. After that, you select your PowerPoint file.
me try again.
You click share. After that, you share your entire screen, or you can share. You can click the window and then you share the application file, your PowerPoint
Yeah,
file.
I have tried both. I try entire screen, then I press the screen share.
Yeah. You still can't share?
There is also still cross line.
I see.
Let me try next time. Inshallah, will work.
Sure.
Share.
If you still can't share, then maybe our IT moderator will share your pre-recorded video. You still can't make it?
Can you see now or no? Not yet.
Nothing.
Okay.
It's okay. Maybe we can ask Leah, IT moderator, to share your Power presentation slide.
Okay.
Is it okay?
It's okay. I
All
don't
right.
have another solution because I'm still pressing the screen, the cross line on the screen.
Have you clicked it? Have you clicked the share screen button at the
Yes.
bottom?
Yes, I click on the screen and then share.
You have to select the entire screen, or you select the window first? Have you
I
selected?
select both.
Okay, or let's say you select window, and then you go and take a look on your PowerPoint file. You have to select the PowerPoint file. Have you selected?
So, okay. Now I select window, and then I click
You select
share.
don't. You select the PowerPoint file first, because you have to select your PowerPoint file. Can you see the PowerPoint that you previously opened in your laptop?
But I cannot see the PowerPoint on this screen.
Okay, it's all right. Have you opened the PowerPoint file?
Yes, the PowerPoint is open.
But you can't see, when you are in the window mode, you can't see your PowerPoint file, is it?
Let me see.
You have to select your PowerPoint, then only you click share. Then the share button will appear.
Okay. Let me try again. Bismillah ya Rabbi.
Can you?
When I open window, I just saw this screen.
Okay, when you select the window, you can see the file, right? In your window, under the window mode, you can see the PowerPoint of your presentation. Can you? You have to select. You have to select under the window. You have to select your PowerPoint file.
The problem that I didn't see my PowerPoint when I shared the screen.
Okay, fine. But you did open your PowerPoint, right? Okay. Okay, you go for your window. You go to your entire screen. Another option, entire screen.
Okay, this is the entire screen.
After that, under your entire screen, you can see the hopping interface, right? And then you try to share. You select your screen. After that, you click share. After that, you go and find your file. Go and find your presentation file, and then you switch to presentation mode. Then we can start. We can see it again.
Excuse me, Dr. Tan, can I say something? Because I already checked this system. Yeah, Mrs. Asma, please at first you click on your PowerPoint slide. At first you click on your PowerPoint slide.
Okay,
Then
this is
you click. Yeah, at first you open again. Yeah, although it is open in your system, but you cannot see at the Windows. At first, now again you click on your PowerPoint slide file open then you go to click on the screen, then you select the window, then you will see. Yeah,
Okay.
please try again.
Window. Can you see it now or no?
No.
Okay, we try one more. Miss Osman, alright, can you refresh your web browser again? This is the last result, I guess.
Leave
Can
and
you
come
refresh?
back.
It's okay. You refresh, you will still in the room.
Okay.
Fine. You refresh and then you share the screen again.
Dr. Tan, he's out.
Yeah, because she refreshed.
Okay.
You start to share again?
Yes.
Still can't?
Did not work. I don't know why.
All right. It's fine. We have the pre-recorded video of your presentation. So,
Will
can you help me? Yeah.
Okay.
It's okay. We play a pre-recorded video. It's fine. Okay, Leah, can you share?
Rahmatullah barakatuh, everyone. This is Asma Obay, a PhD student from chemistry department at University of Malaya. I'm also a lecturer at Jazan University in Saudi Arabia. So I'm glad that I'm participating in the first Malaysian International Conference. And today, inshallah, I will present a part of my project. Let's start. So the title is L-Cysteine capped gold nanoparticles as a chiral recognition sensor for Ketobrophene enantiomers. So meaning that I'm using L-Cysteine capped with gold nanoparticle and use it as a sensor or a colorimetric sensor to detect Ketobrophene enantiomer. So I will go through the introduction, methodology, my project, result and discussion, and finally the conclusion. So let's talk about the chirality and what does chirality mean. So chiral is a Greek word, mean chair, and the configuration of any enantiomer using the can in gold per log priority rules. That rule depend on the atomic number of each individual atom that attach to the chiral center. So this is the chiral center, and by the atomic number of each individual atom, we rank them around the chiral center. And the direction of these atoms clockwise will take R, mean right, and anti-clockwise will take S. So we have S and R enantiomers. Chiral drugs. About 40% of drugs are chiral. So that means the majority of drugs are chiral. Thus consider the chirality a fundamental feature. So in my research, I picked ketobrophene as my analyte. Ketobrophene can control the causes of pain. And because R and S ketobrophene have different pharmacological effect, so I then look for a good selector that can distinguish between R and S ketobrophene enantiomer to achieve the recognition of R and S ketobrophene enantiomer. So after I picked my analyte, which is R and S ketobrophene enantiomer, I thought about finding a quick and easy, simple method for recognition. So recognition of enantiomer can be achieved by colorimetric detection. So colorimetric detection, it's a quick method that based on using nanoparticles, especially gold and silver nanoparticle. So silver and gold nanoparticle have a unique properties like a small size, high surface region, as well as optical properties. So silver and gold can be used directly with the analyte, and this depend on turning into color change that can be noticeable by naked eye. So in my method, I have tried the gold nanoparticle directly with RNS ketobrophene. I didn't notice any change in the color. So after that, I thought about using a ligand. So I thought about cysteine, especially L-Cysteine. So L-Cysteine commonly used with nanoparticle because it has the silver. So silver can bind with the metal surface and form a strong bond. And this bond can interact with only one enantiomer and achieve the recognition process. As you can see in here, so either gold or silver can bind with L-Cysteine. If we introduce the analyte, one of them will turn into color, change the color. So after using the selectant and selector, we need to know how the recognition process will occur. So recognition of enantiomer is based on the capability of any selector to form a complex with one enantiomer, with only one enantiomer. So based on the 3-point rule, which was first introduced by Augustine, suggests that at least 3 active positions of a chiral selector simultaneously interact with at least 3 positions of only one enantiomer. Okay, so we have here this chiral compound and this one. So this one interact with the 3 3 sides of a selector, and this one can only interact with the 2 sides. So this one match and the recognition process occur here but not here. So the methodology, first I synthesize a gold nanoparticle following the Lee and Mitchell method. Then I take part of my solution, my gold nanoparticle solution, introduce L-Cysteine to make L-Cysteine caped gold nanoparticle solution. Then I take 2 ml of this solution and add 100 microliter of my analyte, S or R. So I saw a different color when I introduce R-Ketobrophene, like the color turned to light blue, whereas with S-Ketobrophene there is no change in the color. So after the physical recognition by differentiating the color, I did UV phase to see what's going on. So after the physical recognition, UV phase analysis was done to get more insight on the recognition capability of L-Cysteine caped gold nanoparticle. So as you can see in the UV phase spectra, A is L-Cysteine caped gold nanoparticle. This peak responds to the gold nanoparticle at 536. It's a nice peak. So the gold is spherical. There is a spherical gold nanoparticle. So when we introduce S-Ketobrophene, B is L-Cysteine caped gold nanoparticle with S-Ketobrophene. So no change in the color, as well as the absorption peak indicate that no selective response toward S-Ketobrophene. However, when we introduce R-Ketobrophene, the peak at 536 decreases, as well as we have a new peak at 720. The existence of a new peak can be lead to the interaction between R-Ketobrophene and L-Cysteine and the aggregation of the gold nanoparticle. So meaning that selective response toward the R-Ketobrophene, which was obvious in the color of the solution. So with the FTIR analysis, the spectra of L-Cysteine caped gold nanoparticle show a very broad band in the 3. This band, 3000 to 3500, correspond to the OH stretching and NH3 stretching, and show this peak correspond to the C double bond O stretching and this peak. So when we introduce the R-Ketobrophene, we get the same spectrum. However, when we introduce the R-Ketobrophene, we got new peaks at 2988, correspond to the CH stretching, and this one is the same with like slight shifting, and we got this peak correspond to the CH3 CH3 stretching, and this one correspond to the ester CO stretching, and this peak correspond to the CH3 racking and COH plan bending. This new peak confirmed the interaction between L-Cysteine and R-Ketobrophene, and also confirmed the selective response toward only the R-Ketobrophene. So after I did the FTIR analysis, I did series analysis. So the spectrum of L-Cysteine gold nanoparticle A show this a huge peak. This peak corresponds to the SS band. It's known that most of L-Cysteine tend to form SS band by collision of two L-Cysteine to form cysteine. So this also shows that the L-Cysteine aggregate and it's near to the surface of gold nanoparticle. So in this spectra, it's from 700 to 1600 to show what's going on in this region. So this is the L-Cysteine with gold, and this is when we introduce S-Ketobrophene. It's look the same. This is show the peak of L-Cysteine and the peak of Ketobrophene in Enantiomer. So with our Ketobrophene, we got a new peak at 841, and this two new peak at 1437 and 1462. So this new peak correspond to the CH2 stretching and confirm the interaction between the R-Ketobrophene and L-Cysteine. So dynamic laser scattering and VCM analysis were done to see the size and the stability of gold nanoparticle before and after introducing the Ketobrophene enantiomer. So the size here is 94.50. After I introduce S-Ketobrophene, it's similar, 92. And after I introduce R-Ketobrophene, it's increased to 321. That show that the aggregation, the massive aggregation of gold nanoparticle. Zeta potential also, to get an idea about the stability of the solution. Here it's minus 16.8. And here is minus 15. It's also similar. However, here it decreased to 8.79. So it's not stable anymore because the aggregation of gold nanoparticle. Also, VCM shows same thing with the S-Ketobrophene. There is no much aggregation. However, with R-Ketobrophene, a huge aggregation happened. That's aligned with the UV phase, the appearance of the new peak, with the new peak of the FTIR, with the new peak of the Raman spectra. All show that the aggregation and the selective respond toward only R-Ketobrophene. So this slide proposes an interaction of R-Ketobrophene with L-Cysteine, represent the three-point contact model for chiral recognition and biomolecular system. A functional group of such as amino, hydroxy, as well as carboxylic acid play a key role in the chiral discrimination by electrostatic and hydrogen ligand between the R-Ketobrophene and L-Cysteine. So this indicates a potential theoretical colorimetric detection method for Ketobrophene enantiomer, as illustrated here. So the results show that R-Ketobrophene spatial orientation is more suitable direction than S-Ketobrophene. The Y only R-Ketobrophene can form this ligand with L-Cysteine, not the S-Ketobrophene. So examining the enantiomeric percentage using the purpose sensor is considered a significant matter. Why? Because due to the coexistence of enantiomer in the environment. So because enantiomer exists in the environment as a racemic mixture, so we need to evaluate and do a synthetic sample by mixing a different percentage of R and S ketobrophene. So in this spectra, we have tried different percentage of R and S ketobrophene. This one, A, 0% of R ketobrophene, show the nice peak here, but there is no existence of any peak at 720. So, and then we increase the percentage of R ketobrophene. So B is 25% of R ketobrophene and 75 of S. C is 50-50 of both, and D 75 of R ketobrophene, and E is 100% of R ketobrophene. So this one show so the peak, the new peak here increase, and this one is decrease. Also, I investigate the percentage versus time. As the percentage increase, the absorbance increase. However, it's not related too much to the time. So the C is the mole fraction of R ketobrophene racemic mixture versus the absorbance of this peak to this peak. And this one, the concentration of R ketobrophene versus the difference in the absorbance between this peak and this peak. So in the method validation, I got a nice result. As you can see in this schedule, show the result I got. The linear range between 8.33 microliter to 33.3 microliter. Limit of detection is 2.31. Limit of quantification is 7. I repeat the experiment 5 times, and this the R square of my 2 previous relationship. So in conclusion, the sensor of L-Cysteine capped gold nanoparticle found to be an applicable for recognition of ketobrophene enantiomer, a sensitive, easy, and low-cost method. So finally, thank you so much for giving me this opportunity to participate in the first Malaysian International Conference on Nanotechnology and Catalysis. So if you have any question, I'm here to answer. Thank you for everyone.
Okay, we proceed to Q&A. Is there any question from any participants, evaluators in the room, in the section? You can ask Miss Osma Obai.
Assalamualaikum, Asma.
Assalamualaikum.
Waalaikumsalam. Okay, Asma. It's nice and good presentation. Good job.
Thank you.
Okay. Only I have one question.
Okay.
And this is for your FISEM, right? For your FISEM, they have like a nanostructure, a nanoflower, nanorod, nanowire, right? And for the FISEM, this is look like that is look like what? It means
Spherical. It's spherical nanoparticle.
It's nanoparticle. It's not describe the.
No, it is all spherical, all like circle.
All like. Oh, it's like all the circles because I cannot see clearly in your picture. But
Yeah, you're right because I'm black the picture. So all spherical nanoparticle.
Oh, okay, that's cool.
The
Okay,
average size it's 29 nanometer.
21, 20, right?
29.
Or 21 nanometer.
Yeah.
Okay, so the magnification is around 200 nano for the Fission image.
What?
What is your magnification for the Fission image?
The magnification, I did so many magnification. It's just to see the morphology.
Oh, just morphology.
I'm focusing on the morphology to see the aggregation. So with S, there is no aggregation. With R, there is aggregation. So that's the main point.
Okay. Thank you.
You're welcome.
Okay, good job.
Thank you.
All right.
Mm-hmm.
We will proceed to the next question if there is any.
Okay, I
Yeah,
like to ask. I like to ask one question. Thank you,
You're welcome.
Miss Obaida Asma, for your nice presentation. I just like to know some researchers also used mercury-2 propionic acid as a linker, for any molecules with good nanoparticles. Wherein you use L-Cysteine.
Why? Okay, because L-Cysteine has the S group. So S group can bind with the gold nanoparticle and form a strong bond. That's the reason why I pick L-Cysteine.
Okay. Thank you for your answer.
You're
But
welcome.
mercury-2 propionic acid can also use for binding with S sulfur group. Yeah.
What? Sulfur?
Yeah.
No.
Mercury-2 propionic acid cannot use. Some research are also shown they use also mercury-2 propionic acid to binding the DNA with
there is so many receptors, but I pick L-Cysteine because it's an amino acid and also form a strong bond with my gold nanoparticle. I also try with silver nanoparticle, also form a good bond and give a good result.
Okay, thank you. Next question. You found the size of the gold nanoparticles slightly decrease when you add the ketobrophene.
Okay.
Why? Because after adding any molecules, it have to be increase the size slightly, but in your case, this decrease, 94 to 90. Why? How can you clarify this one?
The stability, you mean?
Yeah. The size of the gold nanoparticles, when you add the ketobrophene, after adding, the size decrease slightly.
No, not decrease. The size of gold nanoparticle alone was 29 nanometer. Okay. After I add L-Cysteine, it's increased to 92. And then I get a similar result with S-ketobrophene. That means nothing happened with S-ketobrophene. But when I introduce R-ketobrophene, it increased to 300 nanometer. It showed the huge aggregation with R-ketobrophene.
Okay, thank you. Just I add here, when you add gold and cysteine, the size was the 94,
Yes.
And when you add S-ketobrophene, that size was the 92.
It is similar. We can see it's similar. 94 and 92 is similar.
Okay.
Yeah.
Thank you.
You're welcome.
Okay. Thank you, Dr. Motalik.
Thank you, Dr. Motalik.
I have one more before we end the Q&A slot. Very quick and simple. Does your sensor, the gold nanoparticle with this the what do you call this L-Cysteine, right? L-Cysteine as a Chiral recognition.
Yeah.
Yes. is it a new combination? Is the first time you produce, or previously has been produced before? Some researcher has produced before this kind of combination as a sensor. Is that a novel thing?
Yeah, some have used the L-Cysteine, different concentration, but this is the first time using L-Cysteine to recognize the R&S Ketobrophene enantiomer.
I see. That means the sample that you produce is considered first time to be used to detect a certain
Ketobrophene.
right?
Yes,
Yeah,
I also use the silver nanoparticle. For silver nanoparticle, I'm the first one to use silver with L-Cysteine as a sensor for also Ketobrophene enantiomer.
All right. So the one that with gold nanoparticle is better than the silver, is it?
So both is good. Both is good. It's just the method validation gives different results.
All right. Is that
Because
different result?
silver is cheaper than gold. So I start with silver and then I try gold.
So that give you a different result, which you claim they have the same good outcome, even though they have different result?
Yes, both outcome. Very good. Easy, simple method. The sensitivity is so high.
All right.
It's just mixing and you get the different color. You can distinguish between R and S Ketobrophene. As you know, the chirality is a challenge subject. And to recognize the R and S Ketobrophene, it's hard. And there is so many research. They use so many difficult method. So this is one of the easiest method to recognize a chiral compound.
Okay. All right. Okay. Thank you for your nice presentations and also your explanation during the Q&A.
Thank you so much
Thank you.
Thank you for having me here. Thank you.
Sure. All right. So right now we will proceed to the next presenter. I will invite Mr. Abu Hashim. So you can turn on your video and share your screen and start to present. Thank you.
Thank you, Doctor.
Yeah, sure.
Can you share my screen?
Sorry? You can share your screen?
Can you share my screen? Can you see my screen?
We can't share your screen. I thought you never provide us
Can
any
you see?
recorder. Okay, you share your screen? We can't see now.
Oh.
Okay. All right, nice. You can put it in the presentation mode.
Yes.
Yeah. All right. Great. Okay, you can start now.
Assalamu alaikum.
You can start now.
And very good morning, respected chair, evaluator, speakers, and participants. Thank you for having me. My name is Abu Hashim. I am a PhD student from Nanotechnology and Catalysis Research Center, University of Malaya. I am going to speaking to you today about electrochemical DNA biosensor for quark detection. The title of my presentation is the development of an oligonucleotide-based electrochemical biosensor for the detection of SARS-CoV using graphene and gold nanoparticle modified skin printed carbon electrode. To begin, the electrochemical DNA biosensor is an important in meat species identification because meat and meat product occupy unique position in our diet, which are highly consumed all over the world due to their appealing flavor and taste. It have immense contribution in growth and development of the body, boost up immunity, especially in children and AIDS patients. It contains high quality proteins with essential amino acids, micronutrients like vitamins and minerals. Also have fats and indirect source of energy, which may be considered as a source of balanced diet. But around the world, approximately 2 billion people are concerned about halal meat due to adulteration. There are many causes of adulteration. Among them, mainly for the purpose of economic pursuit. Impact of food adulteration. Economic consumers are suffer from economic loss. This is not health good for health. There is also religious concern, ethical issue, and also lifestyle. General Food Safety Initiatives in their position paper in 2014 identify cause of food adulteration. About half of the causes are intentional modification adulteration due to economic gain, and another half of are unintentional adulteration due to accidental exposure of infection agents and careless processing. Lots of incidents are available of meat adulteration. See, this horse meat adulteration scandal are very notorious one. World giant food like Tesco, Burger King, Pandas were involved with this scandal. Cosmos in 2014 reported that hot dogs labeled as beef was sold in Malaysian market contain buffalo. Meat adulteration scandal are very notorious. China arrested 900 people with this scandal. Also, China authorities seized 20,000 tons of illegal meat and detained a gang for passing hogs, mink, and rats in as mutton. A report by BBC in 2018 that all kinds of meats are adulterated. Here is shown in graphically. One of the most concerned is the pork adulteration, because pork is harmful for Muslims, Jews, and part of Christian. Different media published news mentioning that pork DNA in halal sauces in Westminster Primary School and pork found in British prison halal food. The name of some media are highlighted in the slide. Falsified meat products are global problem and existing for centuries. But why pork adulteration is so important? Because pork have poor quality meat with high sodium and saturated fat, also for its red meat characteristics. They are carrier of swine influenza, hepatitis E virus, cause of multiple sclerosis, and containing Yersinia bacteria. As mentioned earlier, pork is haram for many religious people, also for economic loss due to mislabeling. That is why attempts have been made for the detection of food adulteration. There are many methods available for precise authentication. These methods can be classified into three groups: physical, protein-based, and DNA-based. physical based method are view based on the external view, and which have very limited use because it is applicable for raw meat only. Protein based method include immunological chromatography, peptide examination, and so on. Protein are heat unstable, so in process meat protein are denatured and it cannot be identified in process meat. DNA based or PCR based method, there are many methods: PCR, RT-PCR, PCR, RFLP, digital droplet PCR, and genome sequencing. These methods are very sensitive, specific, and reliable, but these methods are laboratory based, expensive, time consuming. Sophisticated equipment required trained personnel, not environment friendly, carryover contamination, not suitable for on-site monitoring. On the other hand, DNA biosensors are rapid, simple, portable, easily applicable, selective, and durable. On-site monitoring device, environment friendly, no carryover contamination, applicable for very short DNA target. DNA biosensors not directly used in use. There are very limited use in disease diagnosis, pathogen detection, environment monitoring as aptamer. But in food, for the aptamer are used for orthotoxin, alpha-toxin, and polyphenols like compound detection. Yet application has not been extended for precise authentication based on generic materials. So there is the scope for development of precise authentication tools using DNA biosensor. Based on this analysis, objective of our studies are to develop a short DNA probe targeting cytochrome B gene of mitochondrial DNA and modify that with thiol modifier and carbon spacer arm to facilitate immobilization with modified electrode surface. To develop and validate electrochemical DNA biosensor by fabricating graphene, gold nanoparticles, and DNA probe on transducer surface for sensitive and reliable detection of porcine materials. Methodology: we carried out two types of experiments simultaneously. One is electrode modification, another is probe design. After collecting the skin printed carbon electrode, we studied the electrochemical property, fabrication of SPC with different nanoparticle, characterization, electrochemical sensing ability, study of the modified electrode, precision analysis, and selection of the best combination of nanomaterials. Simultaneously, we retrieved desired DNA sequence from National Center for Biotechnology information with their accession number, aligned with MEGA5 and cluster W to find interspecies conserve and interspecies variable region. Selection of the probe and NC by blast for specificity. Identify model sequence and design specific probe. DNA probe modified with thiol and carbon spacer arm. After that, we combine this probe with modified SPC, electrochemical sensing ability study of the probe modified electrode, then hybridize with our target DNA, and then we analyze and validate the method. This is the overview of our experiment. Fabrication and detection procedure of the electrochemical DNA biosensor shown in here. This is SPC electrode. First, we fabricate it with graphene, followed by gold nanoparticle. Then we immobilize probe DNA. Then we hybridize with target and non-target DNA. Hybrid DNA was intercalated with methyl blue. Based on the methyl blue redox activity, hybridization was analyzed, but through electrochemical method. In this step of electrochemical conductivity was recorded. Probes complementary and corresponding DNA sequence here. This is our probe DNA. We have modified it 6 carbon spacer arm to extrude it from the electrode surface, and a thiol modifier group to conjugate with golden nanoparticle through covalent bond formation. And secondary is the reverse polymer sequence. This will completely hybridize with the sequence. We also introduce several modification on the motivation, like 1, 2, and 3 base mismatch, which is indicated by red color. And we also intentionally include the other 4 species complementary DNA, like cow, buffalo, goat, and chicken. This is the part of an alignment process. We have collected 30 different species from NCBI. We align with them. Here, C for cytosine, T for thymine, F for adenine, and G for guanine. If we see the backbone of the DNA molecule, this is the our selected sequence. It may be mentioned here that this is the complementary sequence. We after modification, we characterize the dielectrode. This is indicating the modified electrode activity, which is determined by the Anderson equation. We characterize the electrode electrochemically by CB. This is the highest peak is for the gold graphene modified species. Also, we characterize it with DPB, like same pattern result, and we also characterize it with electrochemical impedance spectroscopy. Here is a red color indicating that our target modified electrode is showing the least impedance, that is more conductivity. We also optimized our experimental condition. After optimization, we found that optimal temperature for hybridization is 40 degrees, and optimum hybridization temperature. Optimum hybridization time for 40 minutes, and optimum hybridization temperature is 30 to 40 degrees centigrade. Specificity of the electrochemical biosensor. We DPB the DPB voltamogram of the hybridized DNA in the presence of methyl blue for the reverse complementary different types of mismatch and non-target species in oligonucleotide in 10x phosphate buffer. DPB voltamogram of curve of different oligonucleotide. B, peak current histogram of the same oligonucleotide. Here is stand for single stranded DNA, PK for POG DNA, RC for reverse complementary, DS for double stranded DNA, MN for mismatch, the 1, 2, 3, and 3 mismatch, and CW for cow, CF for buffalo, CT for goat, and CK for chicken. From here, we clearly see that the reverse complementary DNA has much higher peak compared to other. This is for single base DNA, and all other DNA has so many minimum peak. This is indicated in the right hand side. This is the peak for complementary DNA. This is for single base messenger. This is for 2, and this is for 3. All other DNA has similar like probe DNA only. Sensitivity of the electrochemical DNA biosensor. Comparison of the DVB response of different concentration of reverse complementary DNA hybridized with work of DNA. Sorry. This is the sensitivity curve. Here we find linear range from nano micromole to 10 picomole, which is much better than any other method mentioned earlier. Reproduction of the biosensor for biosensor. The reproduction of the biosensor is for the good reproduction of the biosensor observed with peak current at 14.45 and relative standard deviation is 2.75. Conclusion: Nanocomposite modified SPC increased surface area by 85% with good conductive properties. The design of pore-specific probe were fabricated on nanocomposite modified SPC. Hybridization and detection process of the pore can differentiate pore from other species, and the biosensor display good linearity in the range of 10 picomole to 5 micromole with a limit of reduction 0.98 picomole. The biosensor exhibit high sensitivity, excellent selectivity, and good stability. Thank you for your kind attention.
Okay, it's okay. Thank you for your presentations, Mr. Abu Hashim. Actually, you are giving slightly more time than what we should give you. Anyway, we proceed to the Q&A.
Yes.
Yeah. Is that any questions to be asked to Mr. Abu Hashim regarding his work? I can call upon.
Yeah, can you access?
Sure.
Okay. Thank you, Mr. Abu Hashim, for your interesting topics sharing with us. I just want to know why you use here screen printed electrode, as some researchers also use other carbon electrode, for example, GC electrodes or other paper electrodes. Why you use here this one?
I have initially tried glassy carbon electrode, but when we glassy carbon electrode is used for several times use and cleaning and washing. When I use several times, it become it reduces sensitivity. That is why I cannot finally use because the result is not stable. But screen printed carbon electrode is only for one time use. It does not interfere with previous result, and it gives very linear output.
Okay, thank you. My next question: why you modified with gold and graphene oxide nanoparticles?
Gold and graphene oxide are very conductive molecule, both are conductive molecule, and they have a very large surface area. due to large surface, they allow binding of or more DNA, and more conductive, it increase our sensitivity. Beside this, we modified probe with thiol group, so that it can make a strong covalent bond with the gold, and the sensitivity become perfect.
Okay, thank you for your nice.
All right. Is there anyone wish to ask a question further from our evaluator, if there is any? All right. I have one more question for Mr. Abu Hashim. I know that you specified there's quite a number of advantages of your work regarding the DNA biosensor, right?
Yes.
So if I would like to just ask your opinions, if I want to highlight what would be your, if there is any, what would be any weakness? I mean, what would be the disadvantage, or maybe some weakness of your DNA biosensor, apart of all the advantages that you said?
Yes. For DNA biosensor, one weakness is the finding proper DNA sequence which will not match with the other DNA. For that, to find out the appropriate sequence, we use bioinformatics tools. We analyze all bases relevant to our food, like 30 bases we have collected, and we analyze them using Mega5 software and find suitable region which will not match with any other DNA in the database. That is, it make it a perfect one. Second weakness is DNA isolation procedure. DNA isolation procedures take around 1 to 2 hours. For application of biosensor, it may be on-site application. It may be a problem.
Okay. All right.
Next question, sorry, doctor. Next part of the question. Hello. Oh, sorry. Since benefit of DNA biosensor is that since DNA is unique, it does not destroy in a high temperature.
Okay.
The DNA is unique. One is the DNA is unique. It does not mess with any other part of the part. Second is in processed food. Most of the food are processed in high temperature, like oven or maybe more high temperature, specifically mince meat. All other components like DNA and other elements fat are destroyed their structure. So that using other method, this type of food cannot be determined. But with DNA is high stable molecule, it does not destroy in high temperature like over 2000 degrees centigrade in oven or in autoclave or any other process. So DNA is the most reliable elements to detect in our food.
Okay. All right. Thank you for your explanations. All right. So I end the presentations for Mr. Abu Hashim. You already end for this slot. So right now we proceed to. Anyway, thank you, Mr. Abu Hashim, for your presentations.
Thank you for the patient hearing.
All right.
My
You can stop sharing.
is longer. I have to make it short, so I do not cover everything properly. Thank you for your attention.
Yeah. You can stop sharing now. All right, so right now I would like to invite our invited speaker, which is Dr. Muhammad Amirul Islam. So you can start your presentation. All right.
Sorry, could you allow me to share my slide?
Yeah, sure. You share your screen. We will project on the screen.
Okay, that means if I go to the slide, then it will be directly
you click
shown over
there's a
here.
monitor screen, right? At the bottom of the hopping interface in the center. You click.
Yeah.
After that, you can see entire screen, window. You select the entire screen. After that, you can see your slide, right?
Okay.
And then you just click.
That means okay. Full screen.
Full screen. You select the screen that you have. Select. Then only you click share at the bottom.
Oh, I cannot understand.
Can you?
So,
There is a desktop sign in your hopping.
sorry, what?
There is a desktop sign in your hopping platform below.
The share.
Oh, I got it. Okay, I got it.
Yes, you click that one first. Yeah.
Okay. Share audio. Okay.
You can see, right? Oh, that's good.
Yeah. Now you can see my slide.
I can see your screen. Yeah. Can you make it at in the presentation slide mode?
Okay, presentation mode. Okay.
Yeah. Okay.
No, now it's okay.
Now it's okay. You can hide the notification. Stop sharing. And beside there, there's a hide button. You can click the hide. You can see there's a notification. Beside the stop sharing, there's a hide, right? You click the hide. Click the hide. Yeah.
Okay.
Yes. All right. You're good to go. Thank you.
Okay. Assalamu alaikum and very good morning to you all. So I would like to thanks to MICNC for giving me the floor to share part of my research in this platform, and also I would like to thanks for being here. So I am Dr. Muhammad Aminul Islam from Department of Electrical Engineering, University of Malaysia. So going to share with you part of my research with the title Synthesis of Lead Sulfide Nanoparticles by Modified and Green Chemical Precipitation Method for Perovskite Solar Cell Application. So we are collaborating with different institute in Malaysia. So here you see the Electrical Engineering Department and also Solar Energy Research Institute UKM and NanoCat in the so an Institute of Sustainable Energy UNITEL. So we are collaborating this research together. So go for my presentation. This is my outline of today's presentation. So first of all, I will give you some brief fundamental of solar cell. I will share with you, and then we go for the review on solar cell, including a perovskite solar cell, and then I discuss about the methodologies in which we fabricate the lead sulfide nanoparticles, and then we will show some results and we discuss it, and finally I will conclude my presentation. So hopefully you will have some information. We'll get some information on about the solar cell and how we incorporate the different types of materials into the solar cell from this presentation. So here is the basic structure, or we call it fundamental structure of solar cell. Most of the solar cell structure is like this. So over here you see because of this is for the thin film solar cell. In case of thin film solar cell, we use the glass substrate, and on top of it we put a transparent conducting oxide. Basically, this is a highly conductive. Almost the conductivity is almost near to the copper metal, and then we fabricate the N-type semiconductor and then P-type semiconductor, and this make the PN junction, which is the responsible for creating the carrier and making the electricity. And then there's a bake surface feed layer because when this P substrate materials absorb the light, here in the junction area there's a create hole and electron. So holes goes through this way and electron comes on this way, and to make it easy collect, so we deposit another layer which we call the back surface feed layer. This is also a p-type semiconductor. On the p-type semiconductor, then we have a metal contact, and you see how the current flow, electron flow from this way to this way, and current flow this way to this way. And of course, the flare rule, which means the main rule play by the p-type semiconductor, which we call the absorber layer, in case of thin solar cell. So here is we have 3 generations till today. We have 3 generations of solar cell. The first solar cell is in 1953, fabricated from silicon wafer, basically silicon. So this development of these types of solar cell we call the first generation wafer-based solar cell, which has also 3 types: monosilicon, polycrystalline silicon, and multi-junction silicon. Even this solar cell already developed, and market share is almost 80% in the market. Till today, the research also going on to improve the efficiency yet. And until 2020, the efficiency for the monocrystalline silicon is 25% reach. And some others is like this. Also, this is the multi-junction, or we call it tandem solar cell, is 40% almost. So here also in figure also you can see this is the monocrystalline silicon solar cell. This is the polycrystalline silicon solar cell. Most of the cases, whatever you see in available solar panels outside, this basically this one, monocrystalline silicon solar cell, because this part is almost 80% market share on this available commercial market, 80% over there. So next generation is start from 1980, around 1980. This is called the thin film solar cell, and this also have amorphous silicon and cadmium telluride and copper, indium, gallium selenide solar cell. And interestingly, this solar cell we can make on top of the glass, or on top of the metal foil, or other flexible substrate. You see the flexible now. Flexible is possible on this thin film second generation. And this second generation solar cell have almost 15% share in the market. And most of them basically cadmium telluride. So why the cadmium telluride we will see in the later. So at this efficiency also have till today is highest efficiency 23.4% for the copper, indium, gallium selenide, and cadmium telluride 22.1%. Even the CIGS has highest efficiency, but cadmium telluride is dominating the market because of low cost and easy fabrication method. So in case of the solar cell, efficiency is one factor, but fabrication technology and then the cost of the total fabrication until the module. So this also play an important role in the commercialization. And now we are in the third generation, which in the lab scale, research is going on. Abundant research is going on about the world. Unfortunately, even they are showing lots of efficiency in the lab scale, but not yet comes to the commercial market. But in the scientific community are expecting very near future, maybe we will see these types of solar cell in the market, and the price will be 10 times lower than, at least 10 times lower than above solar cell, first generation, second generation solar cell. And we hope that the people's expectation will meet over here. So this is also have different types of these also different types. So then we call it the Dysentery solar cell, which is till today 13.0%. This is the oldest solar cell in this third generation, the oldest member. But later on, if organic photovoltaic comes and the quantum dot comes, then their efficiency around 18%. And latest technology comes on the perovskite type solar cell. And you see in the very quickly, this efficiency 25.5%. That's only the perovskite solar cell, which is higher than any one of them. And also then when you make it tandem, like the multi-junction, it comes to 29.5% with the silicon, and when we see AGS, it's 24.2%. But one question is that if even the efficiency in the lab scale is very, very high, why it is not in the market? The answer is that the stability. This solar cell is very unstable. Even in 2 days, after fabricating in 2 days, it can degrade. 100% loss its efficiency because the perovskite materials is not stable under the humidity, light, even on the air oxygen under the air oxygen. When touch it, it degrades. We will see it, and due to this, that means a huge research is going on in the world. Most of the research, I think, maybe among all of types of solar cell, the most research is going on for the perovskite solar cell, making it stable. Because if it will be revolutionary invention, must be, because the price will be maybe 10 cent per watt peak, where now is around cost is for. So this is the things. So also you have a comparison over here. You can see now it's clear to you. So if it is cadmium telluride, CIGS, crystalline silicon, which you call the wafer based one, and perovskite, you see efficiency based when you compare them, both are medium, and crystalline silicon is 25% is high, and perovskite also to above 25% is high. But when you go to the cost related factors, that means raw material cost, finished material cost, fabrication cost, energy payback period, and that means the levelized cost of electricity. So this all the basically related to the cost. You see, crystalline silicon, only raw material cost is low and others is very, very high. So we are now using 80% market share is dominated by these types of silicon, and second is over here. Second is over here. So you see from here also you can get an idea. If we success to make it stable, so there will be a revolution in the renewable energy sector. So over here also you will get some interpretation where the perovskite solar cell is. You see, this all them are basically third generation solar cell. Dysentery solar cell started around 1991, but it still is almost this is certified efficiency. That means last year the published by National Renewable Energy Limited USA, the certified efficiency. So you see perovskite, if you see the perovskite, that means this is the perovskite solar cell start only, you see the over here. So it started very soon. It's from the highest efficiency around 12% efficiency comes around 2015 or not 2015, 2013 or like this. Then on the way very sharply increased to 25.2% now. And also tandem, when it started after 2015, perovskite tandem is not 29%. So rapidly increasing, sharply increasing, where others not do the things basically. So we are main focus is making this solar cell stable under the normal ambient. And here you can see the lab-based solar cell. That's a photograph basically. So its first perovskite solar cell is reported in 2009 with 3.8% efficiency. Now it's come to 25.2% within almost 11 years. So it's a revolution. So we said that the main flare of a solar cell is the absorber layer. And in case of perovskite solar cell also, the perovskite layer is the absorber layer. So this is the main flare. So if we want to understand the that means the stability or efficiency cases, so we have to understand the perovskite structure basically. So here you will see the structure is like this. This is the metal halide octahedra, and it's surrounded by the anion. Okay, coordination anion. So this is called the AMX3 structure. So this structure, where X is the chlorine, bromine, and iodine. Primary perovskite have this iodine, but later on we changed to also some research also changed to complex iodine and bromine or iodine and chlorine, both complex they use. And M is for the metal, and metal is basically the metal cation. With coordinate number 6. So metal cation could be, you see, the lead. Basically, primarily the people use the lead halide, lead iodide. So later on, because lead is toxic, so then they think that we can change to tin and germanium. Tin and germanium. Then also, but one important thing is that when we change to this is the lead to the tin or germanium, the efficiency degrades. So research also going on over here. So how to change the lead is toxic materials to the green or non-toxic materials and get the high efficiency. And also in case of A, we say that A is basically primarily methylamine. Now methylamine lead halide sometimes called. Primarily the perovskite solar cell use this methylamine, but later on people try to this methylamine to change to the cesium, rubium, even formamidine, and also calcium, potassium, sodium. Then also the other materials also could be possible. But one important thing is that whatever you chose the materials for A, it should be larger cation. So each size should be larger than any other. That means atomic radius should be, we have to think about it. So this is the structure basically, also solar cell. So structure also now, okay, we'll go to next slide. Okay, perovskite device structure. When you go for the device, so primarily the invented device structure was this one. So this is the glass substrate and with FTU, and there's N-type. On top of N-type FTU, there's this is the mesophorous titanium dioxide. Then titanium dioxide mesophorous is filled with the perovskite ink, semi-gel ink, and then food the that means this is called the HTM, whole transport layer. Primarily they use the spirometers. This is another organic materials. Then the gold. So this is the normal structure. But when go for the research, then this another three structures comes up, which we call the, this is the normal planar. So this is the inverted. The inverted, that means you see the replace the this that means which we call the this is the ETL, electron transport layer, and whole transport layer, the changing the position. So when the changing the position, we called it inverted. And also in case of mesophorous titanium oxide, we have solid. Okay, no need to have any mesophorous structure. So we have solid layer, N-type layer, and then giving directly to the perovskite layer. This is the perovskite layer, and then whole and others. So when we change the structure to the planar type, we see the efficiency is increased for the planar type than the mesophorous type, even it's normal or inverted, normal or inverted. So in both cases, this is now the so most of the research is going on with these two structure. And here you can see how the carrier is flow. When perovskite layer is absorb the light, is the inside of this layer, perovskite, hole and electron is created. So then we have the whole transport layer collect the hole, and electron transport layer collect the that means electron. And basically this is happening by the band diagram. You know, the valence band or HOMO and LOMO. So then because this is the hole cannot comes over here, it's a barrier. So it should be go over there. And similarly, electron cannot go over there, it should be comes over there, because the energy differences. So by this way, one is blocking and another is permitting. This way we just collect the electron holes in perovskite solar cell, and then we get some electricity from this. So so what is the challenges now? The challenges is must be, first challenge is the stability under the ambient condition. So perovskite films are start to degrade instantaneously when exposed to ambient due to reaction with oxygen, moisture, UV light, and temperature. So this is a simplified equation is over here, how it degrades. So this is the methylamine lead iodide, which is called the perovskite materials. So when it comes to touch to the oxygen or humidity, it absorbs this humidity. So absorb this water molecule, then it's decomposed. You see lead iodide and then aqueous MFEBI. Okay, the methylamine lead iodide now, this one. And this one again decomposed to the methylamine and hydrogen iodide. And every reaction is basically a two-way. Okay, and then again this decompose and then come to iodide, and then this is the gas, and then go water. So you see over here, when you fabricate the perovskite on top of a glass substrate, primarily it's black brown color. So after it degrades, comes over here. So this is the only the yellowish color. Basically, this is the lead iodide. On top of the glass now, only the lead iodide is remaining over here. And lead iodide color is, of course, this is the yellow color. Color is yellow. Okay. So then also another challenge is the replacing the lead. It was some concern also about the lead. So others materials which we will say, and also another thing, how if possible to use another structure instead of MX3. But no research is not yet done, but it's now thinking stage that okay, we can change it any other materials, any other structure who has the who will give the very good efficiency in case of solar cell. And lastly, also most of the cases, the fabricating perovskite using the spin coating process. But spin coating for large scale is not feasible process basically for commercialize a large scale solar cell fabrication. So there's also have another challenges that do we have any process we can develop some processes in which we can large size solar cell we make which if that is uniform with the uniform efficiencies. So by using this, we have priority factors. We have 4 priority factors. First priority was the power conversion efficiency. This having the good and high efficiency higher than the conventional or market, whichever having the market this efficiency. So we already meet this already from the last year. Already we get the 25.5%. So that means it's almost above the efficiency we already get it. Now the priority second is stability and degradation. So this is the among the all priority, basically this is the heart of the all priorities. If it can be met, so other can be easily get. So now research and development community focus on it almost. So to meet this, they change the surface, improve the surface specification of absorber layer or alternative materials and formulation for absorber layer. That means instead of methylamine lead iodide, is there any other materials we can use? And charge transport layers, that means which we call the electrotransport layer and whole transport layer. And our focus is on over here, basically. We want to change spiro-omitted, which is organic materials, to inorganic lead sulfide. So developing lead sulfide. And then another is electrode. In electrode also we have that. So also if we fabricate the solar cell instantaneously, we can encapsulate it. That means making some other layer to save it from the environmental moisture. So that maybe also will improve the efficiency, improve the stability. Then next is the manufacturability. As I said to you that we are using some process in lab which not be possible to make a large size solar cell. So we also have to have a fabrication technique in which we can fabricate a very large, expected large solar cell. And also because large is the commercial factor, before go to the commercial, any commercial people will think about his money. So if they invest to the technology, so it's possible to its bankability is okay or not. Who will take the responsibility if not it does not that is profitable, it does not make it profitable. So that's also you have to think. So these 4 priorities should be met before go to the commercialization to make regulation on solar photovoltaic. So till today, you see as our focus on the HTM, whole transport layer, till today, this is the lots of types of already research is going on over the world. Lots of types of HTM, whole transport materials is used. This is organic HTM, which is the primarily used, but all of them is showing the low stability. But the efficiency is much more higher than any of others doing the efficiency. When you concern about the efficiency, then you can use this. But stability, you cannot get the stability. So you see, spirometer is the primarily used. Later, PSS and other things also. Then also we have inorganic STMs over there, nanoparticle STMs, nickel and copper based, or the fixed type semiconductor based or transition metal based. So our concern is over here, the lead sulfide, the nanoparticles, incorporating lead sulfide nanoparticles as a whole transport material in perovskite solar cell. So here is the limitation basically. I already talked about it, about that means cost and stability. So here you can see the comparison of the cost. So you see these 3 is for the mainly use the organic materials, their cost is too much high in comparison with the inorganic materials. And this is our lead sulfide nanoparticles. This price is per gram is $2.6 only. Among all of them, this is the lowest. And this is you see the chemical book from this, and some of them are from the literature we collected it. Until today, using the inorganic materials, nickel oxide giving the highest 21.66% efficiency and stability, they show stability until 1200 hours. And copper oxide is giving this and the 500 hours. This is giving the simulation. Okay. So what about the lead sulfide? The research is going on. This is not all, much more research is already done from using the lead sulfide. Very few I share over here. And lead sulfide has the attractive feature is that it is direct band gap. It has high absorption coefficient, and most of the important thing is that could promote the perovskite grain growth. That means the grain size could be the perovskite quality also they improve, help to improve will you use the lead sulfide, and it has superior hole mobility, which is very much important for increasing the VOC and fill factor. As another important thing is they had hydrophobic nature. That means it repulses, not attract the moisture, it repulses the moisture. And by this way, you see the 2020 Citric they reported 5.83% efficiency, which is 60 days, 60 days stable. 60 days stable efficiency they reported using this. That means lead sulfide and spark, they use them combinedly. Okay, and also they use, some people also use it combinedly basically, and also you see only the lead sulfide contaminant they say 100 hours, very little degradation. So much more research is needed to explore the way how we can make the stable perovskite solar cell, and also how we can make the lead sulfide as a prominent STM. So here is our methodology. So we are using aloe vera, which is collected from the Hentian Kajang near the UKM, and slice it, and then this is the sink in the DI water and stirs for 60 degrees centigrade. For then we collect the extract. Extract is basically a slightly brown extract, and then we make the lead chloride solution. Then we just incorporate the fluent extract over there, and stirring for 10 minutes. Then we include the thiourea solution of 0.1 mole and heat at 70 degrees and stirring for 2 hours. Stir for 2 hours. Then we filter it with the pore size of 2.0 micrometer, and then filtration, the residue we collect, the solution we collect, and this is all the residue. The other things we discard. This residue is washed by the DI water, and this residue basically the lead sulfide. This is one kind of gel type things. Then we dry it, and then calcination is two different temperatures for 6 hours. And this is our final product. You can see the pictures. And also later on, we just, because we want to fabricate the solar cell, we have to make it to the film. So for this, we also, this nanoparticles will dissolve in toluene with 2 different solution concentration, and then we fabricate this film on top of a FT glass substrate using spin coating, 1000 RPM for 10 seconds, and then 3000 RPM for 20 seconds. And so we go for the, here is our some results over here. So you see the UVBs results is the absorption for the nanoparticles, which has 2. That means one is 300 degrees centigrade and 2 is 360 degrees centigrade. And when you calculate the band gap for these 2, then we got it. The band gap is almost you see 1.91 and 1.82. So the band gap is higher for the 300 degrees centigrade. And also this is the crystallographic structure, but in comparison crystallography, we see the 360 degrees giving the higher crystallography. And also here some also we calculate the crystal size, microcrystal and distribution densities. We see the crystal size also higher for 250 centigrade. So here is the FESM images. We see the grain growth also a bit. Grain also a bit higher for the 360 centigrade, and here's the TEM images. We see that the nanoparticles are not uniform shape, and also the uniform shape are not distributed homogeneously, but the size is higher even again for the 360 centigrade. And here is the EDX. So we see that the composition is different for different 2 different temperatures. And due to this composition, lead sulfide compositional change, Maybe the others change you see as in the XRD and UVBs. We see even on the SEM images again. So and also you see to confirm the crystallographic structure found in this XRD, we do the area in the selected area in the electron diffraction. So from here also we see this is it's the whatever we got the XRD and TEM giving the same results. So after making the film, here is the XRD, which is the same structure. It's retained the structure as the nanoparticles, but the UVB cell a bit change. That means transmission absorption spectra a bit change. But when we calculate the band gap is reduced. And now it's become around 1.5 electron volt. And even also that means the crystallographic structure same, but the distribution density and then microcrystalline that means all the things also a bit change. So it's normal when we go for the, because again we spin coated and we heated the things. So maybe this process has some effect on the when we process the nanoparticles to film. And then also we do some Hall effect measurement to understand the carrier concentration. So here you see the carrier concentration almost 14, which is very good for solar cell application, and mobility also very high. It show. So these two things is very important for us for solar cell. And so now we also implement these characteristics of these layer characteristics to the simulation, device simulation using SCAPS 1D. So here is the structure you can see. Also, you can see an interface of these SCAPS 1D interfaces. This is the structure FTU, PCBN, perovskite, lead sulfide, and we also interface defects and we do. And then we see the IV curve for these things. So we also see that the film 2 giving the better performance than film 1, which is film 2 is 360 degrees centigrade and 1 is 300 degrees centigrade. So we see over here that 360 degree giving the better crystallinity and then also better mobility and carrier better mobility. For these two, basically we get the better performance over here. And also we see over here the parameters basically changing happening in the VOC and fill factor. We know that the fill factor depends on the carrier transport and extraction. That means which is directly related to the mobility. And another thing is that so also then also another VOC is related to the split quasi Fermi level energy, which is related to the basically the carrier concentration and also the band gap, also the things. So also we calculate the capacitance boldness measurement, which we see that which capacitance over here is very higher for 1. So it means that the loss of carrier is accumulated in the interface. So if the interface accumulate lots of carrier, so they basically recombine at the interface, these interfaces. So recombination, if we loss in the carrier in the interface, so its carrier, the VOC and fill factor will be affected, which you see in the performance over here. And also another thing is that we can put the built-in potential. Over here you see built-in potential for the film 1 is 0.55, whereas the film 2, 360 degree series 0.76. This field, the built-in potential directly related to the VOC. So over here we see the VOC is changed over here. So even maybe we have to do more more research on it due to the pandemic. Basically, we don't go to the some others processes or some other parameters changing or other things. Maybe in future we can optimize its process and we will get the better solar cell. Better performance solar cell with high efficiency and high stability. We can do it hopefully. So here is some conclusion already almost things. So we get the high efficiency 27.1% with VOC 0.94 volt and short circuit current 27.75 milliampere per centimeter square and fill factor 76%. So the study confirmed then that lead sulfide process potential for application as an STL for high efficiency and highly stored power solar cell fabrication. So okay, thank you. Do we have any question?
Yeah, thank you. Thank you for your nice presentation, especially regarding your introduction as well as the result. It's a very detailed, very nice. Thank you. Is there any questions that to be asked to Dr. Muhammad Aminul Islam, to our invited speaker regarding his work?
Okay, Assalamualaikum, Dr. Muhammad Aminul Islam.
Yes.
My name is Aida. Doctor, in this, for the perovskite solar cell, how much, Doctor, get the efficiency for that? Because I cannot, how much?
Sorry, but that means high efficiency, how much we get, is it?
Yeah, how much the efficiency for the perovskite solar cell use a lead sulfide?
Oh, lead sulfide till today is highest is, I think we will share over here. So highest is 19.58%.
Okay, 19. Okay.
This one.
Oh, 15, right? 15?
Yeah.
Okay.
Can you see the 19.58%, 2017? The reported by Jang Itian.
Okay.
Is it okay? Anything more?
Okay, no, thank you, Doctor.
Okay. Thank you.
So, is there any other questions, Dr. Motalik? And also from all the participants in the room, if there is any, please. Okay, let me check the Q&A section there. Okay, I guess there is no more, but I have one question regarding your carrier mobility, Dr. Muhammad. I can see that the carrier mobility, the one of the table showing all the carrier mobility. Yeah, this one. Yeah.
Yes.
I can see that the carrier mobility, resistivity, all is getting improved. Is that also influenced by the crystallized size?
Yes, of course. This is related to the basically dislocation crystalline size, even the dislocation densities. You see, if dislocation density increase, so carrier recombination inside the materials will be increased, because it's also giving an indication about the defects of the film, defect inside the film. So if the dislocation density reduce, so that means film quality also increase. So if film quality increase, so it will give a better mobility.
All right. Can I say that the crystallized size, the bigger the size, will improve the overall performance?
Yeah, you can predict it also from from here also.
Oops. I think Dr. Muhammad battery is low, that's why suddenly. Anyway, it's okay. All right. I think I can proceed to the result for the winner of the best presenter in our slot. All right. So now I'm very honored to announce that the best presenter for the section, for this current section, goes to Miss Obai Asma. Miss Obai Asma. All right. Congratulations to Miss Obai Asma Omar. And anyways, all the participants' presentation is nice and it's very nice and very beneficial for everyone here. So once again, congratulations to the best presenter in this section. So now we reach the end of this section, but before I end the section officially, I would like to seek your kind of cooperations to put on your camera. Maybe we have a photo section before I end the section. Oh, not much people. All right, Prof is coming in. I think the winner also, she didn't realize that she got the. Anyways, Dr. Motalik. Okay, it's fine. We can just take we can take the photo session. Wait. I let the Prof come in. There's another one. All right, Prof, you can't see your face.
Okay. Okay.
Okay, so sorry, suddenly my laptop shut down.
All right, sorry, Dr. Mohammed.
Yes,
Yeah,
sorry.
sorry. Yeah, it's okay, it's okay. I just wonder about the question that I asked. Is it the bigger the crystallized size, the better for the overall performance?
Yeah, sometimes you can predict it, but not only solar cell performance not only depends on the crystal size also, but others, that means resistivity, and that means even the crystal size is better. Sometimes maybe defects inside the materials may be high. That means, so in that case you have to measure the mobility also. They have some relation, but it's not straightforward. Some other characteristics also need to characterize, and also some impurity over there to do the EDX and other things also. We can relate it. If the crystallinity is very higher, that means we can predict that the solar cell efficiency will be higher. In generally, we can do it. We can predict it.
I see.
But
the overall result, but the overall result, right? The improvement that you get, right, actually is not really based on the crystallized size, right? It's based on other factor, right?
Yeah,
right?
crystal size also one factor, but there is some other factor also have. I'm saying the things. This is also one factor, not only only one factor. Not about we have to consider other factors also.
All right, okay. I have a simple general question, because you are the expert regarding the solar panel, right? It's just a general question, because around nowadays, right, the solar panel, right, is quite a lot of people, household, they install the solar panel on their as a replacement instead of using the TMB supply electricity. Is it the usage of solar panel is justified with the cost at this point? The solar panel, instead of using the electricity supplied by the TMB, if you use the solar panel, is it for the cost long term? Is it justified?
Yeah, I think so. In the long term, yeah, it has a good effect. Basically, it can reduce your electricity bill, and basically in solar cell, if you have a good solar cell, it could be used for 20 years.
I see.
But one thing is that in the market, the good solar cell founding is that's also another question.
I see.
Because lots of companies on the world, some people does not make follow the standard.
I see.
But yeah, if a good solar cell is that means they can work for 20 years.
But for the cost, initial installment is not that cheap for the solar panel.
Yeah, that's the very that is a very big deal basically, which is a very big obstacle also. The primary cost is very high than others. So due to this, the commercialization is a bit difficult. And we are hoping that if possible to go for the Parvasa solar cell commercialization, this price also reduce at least 10 times. Whatever the research show that.
And also the stability. Yeah, in the stability.
The question is stability. Yes, stability should be at least 10 years stability is needed. 10 years for solar cell.
All right. So we really need the researcher like you to get very good stability, so that all of us can use a very good solar panel next time. In terms of cost,
yeah. Basically, not only me, that over the world, lots of work is going on. Okay.
All right. Okay. Thank you.
Thank you.
All right.
Okay. Thank you all. Thank you all. Okay.
All right.
Bye.